Let's start talking about the three most basic closures for the three terms in the specific Reynolds-Stress transport equation for Reynolds-Stress RANS modeling. And we're not going to talk about additional equations like epsilon and k to make a fully formed set. So the three terms which we identified in a previous video are the dissipation tensor, epsilon ij, turbulent transport tensor Cijk, and the pressure strain tensor pi ij. And these are in the order of difficulty. And let's do that. So we'll look at the most common closures, and the first one is this dissipation tensor. And it was argued a long time ago by Andrei Kolmogorov in the Soviet Union that most of the dissipation occurs at the smallest scales, but we know dissipation affects all scales, as we previously discussed in our two-equation model part of the course. But this is the original or dissipation type closure. So if we believe that dissipation occurs almost entirely at the smallest scales, and there's some local isotropy at the small scales, which I believe to be generally true, then that dissipation tensor, it's a tensor of ij, unlike, say, scalars using k-epsilon models, it'll be 2/3 of scalar dissipation of ij. And here, dissipation is defined in this equation as a viscosity times partial ui, partial xk, partial ui, partial xk prime prime bar. So you'll note that here, there's a scalar quantity epsilon. And it's the dissipation rate which appears in the turbulent kinetic energy equation of the standard two-equation model of Launder and Sharma. And this becomes particularly evident by contracting equation 734, which we've previously shown, and you can form an equation that goes as k is equal to negative 1/2 of tau I, which is turbulent kinetic energy. And with other simple models, we need to establish a procedure for determining epsilon. And most researchers that I've seen are using epsilon as an equation as formulated in the k-epsilon model. For example, Wilcox and Rubison in 1980 or Wilcox in 1988 are computing epsilon by using an equation for the specific dissipation rate. Which is omega in our notation. So you can see that dissipation here is really an anisotropic tensor, especially in anisotropic turbulence, and it's particularly when it's very close to solid boundaries, then anisotropy becomes even larger. So a lot of people have tried to model this effect, and to do that, they might introduce an additional function called f sub s right here. So compare this function with 738. You can see there's just an addition. And so this needs to be calibrated to account for additional anisotropy as we approach the boundaries or maybe even go through shear layers. So we would call this a boundary layer effect. And B sub ij is a dimensionless Reynolds-Stress anisotropy tensor, which we define in 7.41 right here. And here Fs is called the low Reynolds number damping function. It's not because the flow is necessarily Reynolds number, but as you get very, very close to the wall, the Reynolds number should be going down because you're getting close to the viscous sublayer in the flow. And this is chosen empirically. And the empirical choice of Hangelik and Launder in 1976 is shown here. You might say, well, what's the RET? Well, that's turbulent Reynolds number. And the turbulent Reynolds number should become small as we are approaching the wall. Here's the definition of RET right here. So that's the simplest closure for the dissipation tensor. Now it gets a bit harder, and we need to look at the turbulent transport term, which is Cijk. And with other types of equations, pressure fluctuations, it contains triple products of velocity fluctuations, and that's the hardest part to model. And we see that with pressure fluctuations within the fluid, we note that they can't be measured with any assurance of particular accuracy. So there's no experimental data whatsoever, even today I believe, to give us any guidance for modeling the pressure correlation terms. No experimental data for pressure correlation terms. Thankfully, we have direct numerical simulation, and DNS studies help guide us, and they imply we might be able to neglect the pressure fluctuations. Don't be too careful, because DNS is restricted to low Reynolds number simple flows, which are not what we're interested in high-speed flows like in aerospace. So traditionally in the closures, these pressure fluctuating terms are neglected, but I think in high-speed flows, they certainly should not be. And the most common approach for modeling Cijk is to assume a gradient transport process. So one of the first people who did that was Darley and Harlow in 1970, and they proposed a simple rank 3, which can be obtained from second-order correlations of tau ij, which is partial tau ij, partial xk, and they can make the following approximation. Cijk is proportional to partial tau ij, partial xk. So that's a good proportionality, which I think produces some good results. Now you can see this is a very nice and simple mathematical formulation, but it's unfortunately inconsistent because of the fact that Cijk is symmetric in all three of its indices. And it is rotationally invariant, according to equation 737. So to try and reproduce the symmetry and force it in the model for Cijk, Donaldson in 1972 postulated that we can rewrite the equation this way, with partial tau jk partial xa plus partial tau ik partial xj plus tau ij partial xk. So we can compare the differences. So now we can force our symmetry. So now we have a contained symmetry in our basic closure, but unfortunately, it's not dimensionally correct. And it's always good to check the dimensions on the right-hand side of the equation with the left-hand side, so that doesn't pass the check, and you can check it for yourself. So we require some kind of factor for 7.44, which are going to change the dimensions to be balanced, and that factor has dimensions of length squared per unit time. And it turns out that the ratio of k squared over epsilon has those dimensions, which is really good. And so some authors like Meller and Herring and Launder, Rees, and Rode in 1975 multiplied this part of the equation by something like k squared over epsilon times a constant and proposed equation 7.45. So this is a closure that's valid, And here the coefficient CS is constant and it's calibrated to be about 0.11. Perhaps a slightly more general closure was also proposed, not mathematically rigorous, but just by arguments that might go like equation 7.46. So you just compare the two. There's just some extra tensors out here. They're both dimensionally correct on the left-hand and right-hand side, and there's just a new constant coefficient, 0.25 here. So anyway, we'd have to optimize these against some sort of experiments. And it does lump in all the models of, say, the triple correlation with the pressure diffusion term. So they aren't modeled independently. We just take everything on the right-hand side and model it as this one method. So this is probably the most popular and well-known type of closure in 7.45, which I think is preferred because it's a little bit mathematically simpler than 7.46. So that was the moderate difficulty closure, and if you've been keeping track, we still need to close the pressure-strain correlation, which is the third term. That's the pi ij term of the specific Reynolds-Stress transport equation. So pi ij we've already defined in the previous lecture and early lectures on the formulations of the equations, and this is often referred to as the pressure-strain redistribution term. And it's received a lot of attention because it's the most difficult to model. And one reason it's most difficult to model, and also for its importance, is it's on the same order as the production term in the equation, and so it must be important. And secondly, it involves essentially unmeasurable correlations. Maybe they've just never been measured by an excellent experimentalist. For the experimental people watching this lecture, this is a great challenge for you to go and try and measure these in practical turbulent flows, or even simple ones like grid turbulence. So this whole model really relies on trying to seek P prime, or some form of it in the field, and how it's related to U and U prime in the field. And one way to do that in incompressible flows, ideally, is solving the Poisson equation for P prime, and that's in 7.47. And you'll see in this particular equation, we have P prime, and we have U prime, and U, which is mean variables, and of course, correlation, Reynolds stress. So if we can solve this type of equation, say for P, we might be able to get an idea of how P varies in the field of U. And the idea behind that, before we get into it, is that there's some form like P prime equals an integral of a Green's function times the right-hand side. And the Green's function is for this operator here on the left, acting on P prime, integrated over all space and all time. And you can write linear PDEs this way, generally, or nonlinear ones if you assume that you know something about the right-hand side. So if you know the right-hand side of U prime and the correlation, then you can technically solve for P prime by evaluating this integral, even if it's possible to integrate. So we can do this, and this equation, mind you, which I didn't mention its formulation, is from the divergence of the Navier-Stokes equation, and then using the continuity equation and subtracting in the time average from the instantaneous resulting equation. Now, in compressible flows, these operations will lead to a transport equation for the divergence of U prime, that is, partial Ui prime partial Xi. So in equation 747, it might depend on partial Ui prime partial Xi 0, which isn't true in compressible flows. So we have problems in compressible flows, excuse me. And this is definitely consistent with the fact that the pressure signals travel through a fluid at the speed of sound in incompressible flows, but they travel at infinite speed if it's an incompressible flow. So therefore, we would expect that the fluctuating pressures to be governed by an elliptic equation, such as equation 7.47 for incompressible flows. but that wouldn't be true at all for compressible flows. And really, in all flows, even if we look at them incompressible, we would always have a speed of sound and compression waves traveling through the fluid at, say, the local speed of sound. So therefore, we should expect the pressure fluctuations to satisfy a transport equation. I hope. And that's typically hyperbolic in nature. For compressible flows. So don't confuse Poisson equation with a potential transport equation. So as I mentioned, you can solve this with a Green's function. We'll note that in a few seconds. But before people use a Green's function to solve 747, they would divide 747 into two parts. P prime slow, which is called the slow term, and P prime rapid. And don't take these names too literally. And so P prime is the sum of two contributions, and then they would try and construct two equations. They would take 747 and based on this, divide the terms in two ways so that we can still add the left and right-hand sides in terms of P prime and P prime rapid and get these. So now we have two equations which satisfy 747, and we could solve them independently and sum their results to get P prime, which is the relation between prime and these variables. So you'll see in general there's a notion by the nomenclature that we talked about, and it means that changes in the mean strain rate contribute immediately to P prime rapid. And that's because there's a mean velocity gradient which appears exactly in equation 750, which is right here. And you don't see that in equation 749, which is the slow pressure equation. And in 749, which is the slow equation for pressure, we might see that there's some slower or indirect effects occurring from u primes into the slow variable. So the terminology between slow and rapid shouldn't be taken literally, because in real flows, there's a mean strain rate does not necessarily change more rapidly than, say, the Reynolds-Stress. Now, for homogeneous turbulence, these equations can be solved in terms of appropriate Green's function. That is, there's a free space Green's function for pi ij, and we might divide the solution into two parts for free space turbulence, like grid turbulence, and you have a free space Green's function. So here we show Aij and Mijlk separately. So Aij is the contribution from the slow pressure strain rate, P prime slow, and that's right here in 751. And then there's a tensor, which corresponds to the rapid change, which we just discussed a few seconds ago of pressure strains, and that's Mijkl times partial UK partial XL, where capital U is the mean variable. Now you can see that this is a closed form solution, but in practice we would have to know everything inside the integrand exactly, and we would have to integrate it over all space. So we would have to integrate every point in space to calculate pi ij in all time. And that's a very expensive calculation, and it's probably even more expensive than DNS, because I've done these types of calculations for aeroacoustic work from Turbulence. Now, this is for homogeneous turbulence, but we're interested in, homogeneous turbulence. We're interested in inhomogeneous turbulence. So we need to look for the second terms in particular in 751, Mijkl, and right here. And we'll note that integration now involves the mean velocity gradients. So we should take a second and look at some of the single shortcomings, the single point closure schemes. So single point schemes are nice because they're easy to work with mathematically and implement, but they don't capture flow history. And you can see equations 752 and 753 are really two-point relations because you're looking at integration between every 2 points, vector x and vector y, which are any two vector points from the origin in your turbulent field. I can't stress this enough. So this is really a two-point formulation, even if it's homogeneous turbulence. And we might be able to close that because we know and understand two-point closures for homogeneous isotropic turbulence. So we might be able to accomplish correlation or closure for the correlating terms based on some physical location if we make some assumptions. Now the pressure-strain correlation is obviously not localized, which I just pointed out in equations 752 and 753. It involves contributions from every point in the flow. So what does that imply? It means that the products of fluctuating pressure involve two-point separations. And therefore, we would expect modelers to assume that the turbulent flows behave as though they are locally homogeneous, and then we would use equation 7.51. But we would also expect that there's some kind of contribution from more than one or two large eddies in the flow to be negligible, which is good. Like if two eddies are very, very, very far apart, they would be uncorrelated, and so we could limit these integrals to be somewhat locally over the largest integral scales. This is sort of a bit of hand-waving, but it allows us to try and focus on local turbulence, if you will, using two-point correlations. So these tensors ij and mij at KL will be, once again, looking for symmetry and must also contain mass conservation and other constraints. For example, this trace of pi ij must vanish from the symmetry, and this must be true for both the rapid and slow parts of the breakdown of pi ij, slow and rapid, on the first and second term on the right-hand side, respectively. So there's a few postulates on how this might be done, and these are fairly crude, and there's really no way to verify them except through DNS, but as I mentioned, DNS is only for low Reynolds number flow. And RADA, which is the second closure for specific Reynolds stress transport equation models, assume that the slow part of the process, which would be viewed as the return to isotropy term, might go as Aij as a constant C1, which is a closure coefficient, times the dissipation divided by turbulent kinetic energy times the sum of tau ij Reynolds stress plus 2/3 K turbulent kinetic energy times Kronecker delta function. So these was calibrated for measurements of, say, like grid turbulence and other types of fields. So now that we have this term, this is the first term of equation 751 right here. We need to try and close the second term. So that would be called the rapid strain term. And in the 1960s, late 1960s, early 1970s, there was a lot of research, and it assumed that it's negligible compared to the slow term. And that's one viewpoint. On the other hand, Crow and Reynolds gave simple examples of turbulent flows for which the effects of the rapid strain term far outweighs the slow term. So these authors neglected it, and I don't think that was a good decision other than for convenience. So let's write Crow and Reynolds. This is not Osborne Reynolds, but someone else with the same last name and at the same time frame showed that the rapid term dominates sometimes. And other authors later on tried to devise particular closures to approximate the equation based on kinematic theory. And one particular way they picked it up, Launder et al. In 1975, if you want to Google it, wrote MIJKL in terms of a tensor AIJKL and broke it apart this way. And this would be valid for homogeneous turbulence. And this tensor, if you break it apart this way, must satisfy symmetry and normalization constraints, which are listed here and here. And then Launder came along and proposed a closure for AIJKL. And if you have AIJKL, you can find AIJKL from symmetry and normalization terms. And here's the full model. And you can see it involves nothing but closure coefficients, like alpha, beta, C2, eta, and V, and Kronecker delta functions, which we just noted again. Delta ij is 1 for I equals j equals and 0 otherwise, and particular stress terms, and times turbulent kinetic energy. So the scope of this class is not to necessarily re-show their model, but they partly chose it because all these coefficients can be related to each other in terms of one coefficient, C2. So they really only have one calibration coefficient. And their model can be summarized as one of the first closures that was put in an exercise against CFD codes and experiments in the 70s. They're incredibly expensive computations. And that's summarized here as the LLR model, which stands for Launder, Rees, and Rode, 1975. And here's the summary of their model in 761 to 763. They have their rapid pressure term of pi ij. And we've put in these coefficients, which can be repeated from their paper. So you need to look at this paper for the full justification and the derivation. So as I mentioned, the amazing thing about this model is there's only one real closure coefficient for the terms in the rapid pressure term of pi ij. The value of C2 comparative experiments is found for homogeneous isotropic turbulence, and in their original paper they each suggest a value of C2. But you have to choose a constant, it will be 0.40. And the model is revisited later, about a decade later, by Morris, 1984. And he looked at values of C2, 0.50. And you can see a lot of authors have prescribed a lot of different values in ranges saying could be anywhere between, say, 0.2 and 0.6. So if I only have one closure coefficient, it's hard to find particular excellent closures. There's been a lot of other types of models and attempts for these. Bradshaw in 1973 has shown that there's additional terms which could be put into the models that affect the pressure fluctuations near solid boundaries. And those are really attributed to like mirror images. Just like you have acoustic waves near surfaces, you can find reflections and symmetry solutions. Well, that's the same type of pressure fluctuations that would appear in the pressure strain term. So that's like an acoustic analog. And in the turbulence community, I believe these are referred to as the pressure echo effect. There's one way, and it might be an image, as I just mentioned. So Bradshaw and others modified the pi_ij model with what they call a wall reflection term, which is right here. And it's slightly different. So they would find pi_ij with sup w to mirror the wall. And bij is remaining the same definition. So it's really a modification of the model. There's been other work, for example, Lumley in the late 70s looked for closure approximations that have used nonlinear relations and expansions in terms of anisotropic tensors. And those are the major three closures traditionally for the Reynolds-Stress term. Thank you.